All right, in this video, we're going to talk about 9.3, the integral test and the p-series test. And our objectives are going to be to use the integral test to determine whether an infinite series converges or diverges. And we're also going to use properties of p-series and harmonic series to determine convergence or divergence of infinite series as well. So let me just make a note here before we continue. Always ensure that you adequately justify using a test when required. So if a test has conditions that have to be met, you must show that all the conditions of that test are met to use that test before just jumping in and using that test. You're going to see now why we spent so much time talking about integration in part two, in the second big topic of calculus before we got to this, because of the integral test, because of the relationship between infinite series and integrals. We already knew about that relationship with Riemann sums, and we're going to take advantage of that now to kind of tell whether a infinite series converges or diverges by looking at the related integral to it and saying that they're going to have the same behavior. So this is our a test that tells us whether a series converges or diverges. It will tell us both answers. This convergence test applies to series with positive terms only. So we need to make sure with the integral test that if f is positive, continuous, and decreasing, there's our three conditions. Condition 1, condition 2, and condition 3, that we have a function f that is positive, continuous, and decreasing for x greater than or equal to, I'm going to actually say that this is going to be a little a down here. It doesn't really matter what that number is down here. X greater than or equal to a. Actually, let me call it k, for no good reason other than k. It's easy to turn a 1 into a k. All right. To infinity, like that. And an is equal to f of n. Then if I have the infinite series from n equals k to infinity of an, and I have the definite integral from k to infinity, f of x dx, it will say 1 on all of these things in the book. I'm just telling you, it doesn't have to start at 1. It could start at 2 or 3 or whatever. There just needs to be a lower limit here where from everywhere greater than or equal to that number, that is positive, continuous, and decreasing. If I can show that, and I can maybe even need to peel off a certain number of terms here to make that happen, then I can look at this this integral, and if the integral converges, then the series converges. If the integral diverges, then the series diverges. They both do the same thing. They both converge or both diverge. They don't necessarily both converge to the same thing when they converge, but they will have the same convergence or divergence behavior. So again, before applying the integral test, justify your choice you must show all three conditions are met. Condition 1, f of x is positive for all x greater than or equal to k. 2, f of x is continuous for all x greater than or equal to k. And 3, f of x is decreasing for all x greater than or equal to k. You must show all three things. Okay? If you don't show those things, you're not allowed to jump in and just start using the integral test. So consider the harmonic series. Summation from 1 to infinity of 1 over n is 1 over 1 plus 1 over 2 plus 1 over 3 plus dot 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 plus 1 over n, which diverges, and we'll show it using the integral test. Let's first try the nth term test. We're told to always try that first. Limit as n goes to infinity of 1 over n is equal to 0, so we have no info from this. Let's keep going. Let's try the integral test. Letting f of x be equal to 1 over x for x greater than or equal to 1. And we can't just draw the graph and look at it and assume that these conditions are met. First is f of x positive. Sure, let's make a sign chart. So we have a vertical asymptote at x equals 0. We have no zeros in the numerator. So when we stick in anything in the interval of negative infinity to 0, we get something that's negative. A positive over a negative is a negative. When I stick in anything to the right in the interval of 0 to infinity, I have a positive over a positive is a positive. Everything that we're interested in from 1 to infinity, here's 1, is in this region where it's positive, since f of x is positive for x is an element of 0 to infinity, and 1 to infinity is a subset of 0 to infinity. F of x is positive for all x greater than or equal to 1. Zero. Let's just say it that way. F of x is positive for all x greater than or equal to 1. All right. 2, is it continuous? Recall that rational functions are piecewise continuous on their domain. The domain of the function here is negative infinity to 0, union 0 to infinity. Since 1 to infinity is in the domain of f, f is continuous on 1 to infinity. The only discontinuity is at x equals 0, which is not in 1 to infinity. All right. 3, increasing. So we're going to use the, decreasing. So option 1, which I don't like as much. Option 1 is what we did last time to show a sub n plus 1 is less than or equal to a sub n for all n. But the next term is always less than, and we need to say strictly decreasing, so we can't say or equal to, we need to say strictly less than for all n. Option 2, which is the one that I like. So I'm going to put a star next to this, is to show that f prime of x is less than 0 for all n greater than or equal to our k value of interest, which is 1 here. So let's find the first derivative here. F prime of x is equal to negative 1 over x squared. I look at my first derivative. We've got my vertical asymptote at x equals 0. This interval from negative infinity to 0, and this interval from 0 to infinity. When I stick in a negative value here, I get that it's decreasing here. When I stick in a positive number here, I get a negative value and it's decreasing over here. So that means that this is definitely decreasing on the interval from 1 to infinity. For all x greater than or equal to 1. So we have shown f of x equals 1 over x is positive, continuous, and decreasing for x greater than or equal to 1. So we can use the integral test. I think you're already getting the idea that this is not one of our favorite tests because of all the prep work that we have to do. So let's see what happens 1 to infinity of 1 over x dx. We're going to have to say that's limit as b goes to infinity of 1 to b, 1 over x dx is ln of the absolute value of x. Limit b goes to infinity, 1 to b is going to be equal to limit b goes to infinity of ln of the absolute value of b minus ln of the absolute value of 1. That's 0. This approaches infinity, so it diverges. And because the integral diverges, series also diverges. All right. By the integral test. All right. Apply the integral test to the series. N over n squared plus 1. So let's think about that one. No asymptotes, but I do have a 0 here to consider for f of x equals x over x squared plus 1. And so the bottom is always going to be positive. And this is negative, and this is positive on that side. So this is negative, and this is positive on this side. So from 1 to infinity, we are positive on 1 to infinity. Check. Let's find continuous. So no discontinuities. For f of x equals x over x squared plus 1. So continuous everywhere. Including the interval 1 to infinity. And then let's find f prime of x using the quotient rule, equal to derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared is equal to x squared plus 1 minus 2x squared over x squared plus 1 squared. That's a negative x squared plus 1 over x squared plus 1 squared. So that's the same as negative x squared minus 1. When I pull that negative out front, squared plus 1 squared is a negative x plus 1 times x minus 1 over x squared plus 1 squared. So my sign chart for f prime is a negative 1 and a 1 for my critical numbers. And I have a negative that's in my formula. My denominator is always positive here. And so if I stick in something to the left of negative 1, so negative times a negative times a negative is a negative over a positive is a negative. So this is decreasing. then I'm going to have a negative times a positive times a negative is a positive over a positive is a positive. So this is increasing. And then to the right over there, I have a negative times a positive times a positive is a negative over a positive is a negative is going to make this decreasing so I'm increasing from -1 to 1. I'm decreasing on negative infinity to -1, union 1 to infinity. There's my interval of interest from 1 to infinity. So I'm increasing on 1 to infinity. So check. Positive, continuous, and decreasing, sorry. Why do I keep saying increasing? I mean decreasing. Decreasing on 1 to infinity. All right, so positive, continuous, and decreasing. So I get to use the integral test. So let's set it up. Interval of x over x squared plus 1 dx from 1 to infinity. And I'm going to do a u substitution here. U is equal to x squared plus 1. Du is 2x dx. So let's make that a 2 and a 1/2 there. And that makes this 1/2, 1 to infinity. I'll fix that with u's in just a second. Du over u. If x is 1, u is 2. 1 plus 1 is 2. All right, so this is going to be equal to 1/2 limit as b goes to infinity of 2 to b of du over u. It's 1/2 limit b goes to infinity of ln of the absolute value of u evaluated from 2 to b. 1/2 limit b goes to infinity of ln of the absolute value of b minus 1/2 limit b goes to infinity of ln of the absolute value of 2. This is going to infinity minus some number, but that's still going to be infinity. So this diverges. So the interval diverges. Therefore, that's a shorthand for therefore. The series also diverges by the integral test. Okay. Let's look at the series 1 over n squared plus 1. Start with the nth term test. Limit as n goes to infinity of 1 over n squared plus 1 is 0. There's no info from this. It's not geometric. It's not telescoping. So we're going to go ahead and we're going to try the integral test. So is it positive? We have no zeros and no asymptotes. So for f of x, just stick a number in as a test point. F of 0 is equal to 1 over 0 plus 1 is 1 over 1 is 1 is greater than 0. So we're going to be positive for all real numbers. So yes, positive on 1 x greater than or equal to 1. Let's continuity. There's no discontinuities. So continuous on x greater than or equal to 1. First derivative here is going to be if f of x is equal to 1 over x squared plus 1, f prime of x is equal to a negative x squared plus 1 to the negative second times 2x equal to a negative 2x over x squared plus 1 squared. That's going to give me a 0 of that at 0. Prime of x. The bottom is always positive. So this is going to be a negative over positive is a negative, and it's going to be decreasing here. A negative times a negative over a positive is a positive. It's going to be increasing over here. So it's going to be decreasing on x greater than or equal to 1. So 1 is in there. So check. So I'm allowed to use my integral test. Integral from 1 to infinity, 1 over x squared plus 1 dx. Limit as b goes to infinity of 1 to b, 1 over x squared plus 1 dx. Its limit as b goes to infinity of arc tangent of x evaluated from 1 to b, limit as b goes to infinity of arc tangent of b minus arc tangent of 1 is going to be pi over 2 minus pi over 4 is pi over 4. So this converges. Therefore, the series also converges by the integral test. Let's go ahead and look at P series and harmonic series. So a series in the form of summation from n equals 1 to infinity of 1 over n to the p is equal to 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus dot 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 plus 1 over n to the p is called a P series. If p equals 1, the series of series from n equals 1 to infinity of 1 over n to the first, that would just be 1 over n. It's called the harmonic P series. So what are the conditions for convergence for a P series? The P series summation from n equals 1 to infinity of 1 over n to the p converges for p greater than 1 and diverges for p uh, uh, greater than 0, but less than or equal to 1. And I kind of talked about that a little bit ago. Actually, just usually we say p less than or equal to 1, because if it's negative, then it's going to go up here, and then that's going to go to positive infinity. So we can just say, we can actually just say p less than or equal to 1, like the textbook does. Because a negative exponent in the denominator, that's going to go to the numerator, and then it's going to blow up to infinity. All right. P equals 1 is the harmonic series. So it diverges by the P series test. It's enough justification to say it is a P series with P equals to whatever. So justification is going to look something like P series with P equals to fill in the blank here. Thus, the series, pick whether it converges or diverges by the P series test. Not going to make you know a theorem number. All right. So divergent P series. Example here, does the series 1 over n to the 1/2 from n equals 1 to infinity converge or diverges? So this is a P series with P equals 1/2. Since 1/2 is less than or equal to 1, this P series diverges by the P series test. Now let's look at this one. I'm going to have to rewrite n equals 1 to infinity of 1 over n to the 5th. This is a P series with P equals 5. Since 5 is greater than 1, this P series converges by the P series test. The reason we talked about the integral test first before the P series test is because there is a way to use the integral test to prove the P series test. I mentioned that in chapter 8 that there was a integral for 1 over x to the P dx, and we said that we knew that this converged when P is greater than 1, and it diverges when P is like that. I'll go ahead and I'll get rid of this that I covered up. That those are the conditions for that. And so because this series is related to that integral, I can use the integral test because this would meet the conditions for the integral test being positive, continuous, and decreasing. And it would have the same convergence and divergence rules. Therefore, I can just make its own test and skip all that and say, if it's in this form, I know it's positive, continuous, and decrease, and I know I could use the integral test. I know I could use this theorem of integrals. So let me just go ahead and go straight to the conditions for convergence and divergence for this integral and say that they apply to this type of series as well. So where the integral test is a really difficult test to use because I have to show positive, continuous, and decreasing, I don't have to show that for a p series because I know that every function in the form of 1 over n to the p is going to be positive, continuous, and decreasing because n is always going to be a positive number. There's not going to be any discontinuities here in the domain because I'm not going to be starting at 0 here. I'm going to be starting at 1. And let's see. So that's it. And I can, there is a proof for that in the textbook, both back with the this integral in chapter 8. There's a proof for that in the textbook. And there's a proof for this in the textbook as well, if you would like to see them. But I'm not going to show them to you. All right, that's it for this video. We'll come back next time and we'll start talking about comparison tests, both the direct comparison test and the limit comparison test for series. Very, very powerful tests that we like to use a lot. So let's come back and talk about that next time. See you for the next video.